Hello students, this is the second session of introductory session to the groups. So today I will talk about simply the binary operations. So what is a binary operation? A binary operation is denoted by star. It's not a star, actually it's called asterisk. Is a non-empty set of S, is a rule that assigns, it's a rule, so that assigns to each of the ordered pair of the element of S and uniquely determined element of S. So ordered pair and uniquely determined. So what is unique? 1 determinate, uniquely ordered pair, 5 greater than 4 greater than 3 greater than 2 greater than 1. Simple structure. So the element assigned to the ordered pair A greater than B. So maybe A greater than B or A less than B, but A and B are not equal, where both of them is a part of S. Then we denote them by this. So this is a binary operation. So in other words, a binary operation of the set S is a map or a function where S cross S leads to S from the Cartesian product. We can talk about an example. Let's see. Okay, I will try to make it as easy as possible. So let S equal to natural numbers 1, 2, 3 dot dot dot. So we define the binary operation on S, that is A cross B, and I talked to you about a function that is maximum of A comma B. So example 2, 3 is nothing but 3. 3, 3 both are same. So 3, even 3, 2 ordered pair, both are giving you 3. We can define our binary operation with respect to this as A dot B is A. So 2 dot 3 is 2, 3 dot 2 is 3. So what happens, it is the first value becomes the answer, first value becomes the answer, first value becomes the answer. This is a way to define. Even we can define a binary operation with respect to this, the triangle or the difference operator type of thing. So this is equal to A to the power B. If they say you that the binary operation define relationship this, so they may tell you that 2 plus 3 equal to 2 square. If it is given that A plus B equal to A square, they can't use this plus. That's why they are using this asterisk, which is not plus, minus, into or divide. Okay, so this is not a simple mathematical structure, so you don't have to worry about things. So if it is 2 and 4, this is simply 2 to the power 4. So if it is 3, triangle 3, 3 cube, 27, and this is 16. After this you can go on a normal mathematical way, but this is the way to talk about a binary relationship. I hope I made myself clear. Important points about the thing, that it must belong to S. So whatever you are getting from a binary relationship, it must belong to S. Second thing, the operation must be defined for all elements. This is must be defined. Second, for all elements. So this fails for the example if I say A relationship to B, A inverse B A on real plane, as the matrix A inverse does not exist in this structure. The result of the operation must be, remember that, every time uniquely determined. If we say that if the set A cross B and where C square equal to AB, and so far for A equal to 2, B equal to 2, C may be 2 or minus 2. You getting my logic? So as they are not uniquely determined, this is called uniquely determined. So if you are getting a value, then it must be a unique value. So in the books they always mention it like this, keeping in view that this is very bookish way. So I'm trying to break all the barriers of uniquely determined structure, or what is a group, what is a formation. So we can talk about any other examples. For example, A relationship to B where C greater than equal to A plus B plus 5. This is not a binary operation, as A cross B is not unique. So if this thing is not unique, we cannot proceed. Not unique means more than one possible cases can lead to this thing as well. Okay, remember that number of commutative binary operations of a set is, so the number of commutative binary operation of a set, they may ask. So let S be a finite set, cardinally finite, okay, that is this thing equal to n. So for the commutative maps we require that PQ and QP must be mapped to the same and value by the map. So remember that the domain, so whatever is the domain of the commutative map, that will have n into n plus 1 by 2, and it will have n into n plus 1 by 2 commutative binary operations. So they may ask you a numerical questions that in a simplistic structure of binary operation, how many binary commutative operations are there? So the answer to this question directly comes to this. Okay. Now we will proceed to the next one, and remember that there are associative properties are always with this, which we have done in the lecture number 1. Okay. Now what is a semigroup? So semigroup is nothing but a set equipped with associative property. Associative binary operation is called a semigroup. For example, n and plus, natural numbers with plus, natural numbers with the property of multiply, natural number with the property of LCM, natural number with the property of HCF, in that way. But the binary operation defined in any other way may not form a group based structure. So we will go to those examples very soon where the binary operation will not be forming any semigroup. What is associative powers? So these are very well used, well versed things, but many of us do not know exactly the meaning of this. Remember that for an associative binary operation, so I have explained what is associative, I have explained what is binary operation. So now that thing, remember that it's not a into plus, it's any kind of thing can be happen. Okay, so for this binary operation on a set, and the set is defined by S, and a natural number n, we define that a to the power n is a. How many times? N times. But here it is not a multiplicative structure. Let me give you an example with respect to numerical idea. So let this equal to this and s equal to p of r. F belongs to function of r and is given by fx equal to 2x plus 3. Okay, where x belongs to r. Then if q of f of r is function by what? So f of q of x. So remember that it is mathematics, but not in a very class 7-8 type of direct mathematics. So here we are putting this thing, and remember that we have introduced this asterisk with this function. Okay, so this is f of x. Now you can apply basic mathematics. So that is 2x plus 3 plus 3 plus 3. So this is 8x plus 21. That's it. So this is the basic theorem based pattern. And remember that even if it is like this, so according to this, so we can say this a star dot 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 star 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 asterisk. So every time this is m times, this is m times. So m times a star is coming. So this whole thing is m times, mn times rather say. So a mn. That's it. So this whole thing is coming n times. So a group of properties is coming n times, and each of them is offering m times. So the whole thing comes mn times. Okay. Next, another important part, monoid. Monoid means a semigroup. A semigroup is called a monoid if there exists an identity element for the binary operation defined on the set. That's it. Identity element on the identity element for the binary operation on the set. That's it. So quite a straight cut structure here we can give it. So remember that n plus is not a monoid, but n dot is a monoid. So binary operation, this is not. Okay, so and remember that there has to be an identity element. In case of pluses, so if we say like 2 plus 1, it gives you a 3, but 2 into 1, that gives you 2. So that's why I is still considered as an identity element, because E equal to A for all values of A, that is for S. So identity element is not changing the pattern. So can we say, let's talk about some monoid based idea. What we can say, yeah. So 1, 2, 4, 8, 16 with the LCM and E equal to 1. This will form a monoid. Okay, so if we take the LCM, 1 is into the consideration. And even in case of matrix also we can see a monoid structure is also coming. So we can see that there has to be an existence of the identity element. Okay, so remember that. So what is this group? Is actually group is not a group, is a set, but a non-empty set together with a binary. So it's a set, it's non-empty. You have the binary operation. Even for multiple values you can have the binary operation taking 2 at a time, usually called a multiplication, that assigns to each ordered pair. So there must be an ordered pair of the element of G, and element of G is denoted by AB. Okay, so we say that G is a group under the operation if the following 3 properties which I am going to tell you will be. The first is associative, that is the operation must be associative for all values of A, B and C into G. If we say that for example A, B and C is A of B, C. Second is existence property, existence of identity. So there is an element that's called the identity element for which AE equal to EA. That's it, for all values of A belongs to the group. And the third one, associative identity inverse. That's it. So associative identity and inverse. Don't need to remember anything else. So there must be an element A in G for all values of this, and element B in G is called the inverse for such a way that AB equal to BA gives you the identity element. That's it. So a group is said to be a finite group. How did make it a finite one? Finite group if the number of elements in G is finite. That's it. So the number of elements is G is called the order. So number of element in a group is called the order. Okay, like the stick we play golf is called the club. That's it. It's not the place where we go and play golf. That is also called golf club. But actually club is that stick by which you play golf. Okay. And remember that the finite group, the number of elements of the order is denoted by modulus G. So if G is an infinite set, then we said that the group is of infinite order. Okay. So if the finite group has a small order, then it is convenient to prove that the group using a Cayley table, C-A-Y-L-E-Y. So what is a Cayley table or a multiplication table? So how do we do that? The basics are not again discussed properly in the books. So this is the operation structure. You can take it as a simple multiplication. This is G1, G2 dot 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 Gn. And this is G1, G2 dot 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 Gn. So first one is G1, G1. Second one is G1 start G2. So this G1 asterisk Gn. Then G2 asterisk G1. Then G2 asterisk G2. Then G2 asterisk Gn. In this way we are proceeding, and the last one has to be Gn, Gn. Okay. So this is the pattern, very easy. It's just like log x equal to log y, so x equal to y. We can write it, but how we do that? So this is actually, we are taking anti-log and then we are cutting, but we are writing it directly. So the entire group theory based pattern is whether you talk about this या फिर आप डायरेक्ट लिखते हो. Okay. Next we will talk about group of numbers. So let G equal to G1, G2 dot 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 Gn. Okay? And let this be the binary operation. Okay? So remember that if I give an example, the set of integers, set of rational numbers, set of real numbers, set of complex numbers forms the group with addition as binary operation. They form a group. In each case, here we can take 0 as an identity element. In case of addition, 0 is an identity element, not 1. And inverse of an element x is, inverse is denoted by minus x. So z comma plus, q comma plus, r comma plus, and complex comma plus. So these are all binary operations with respect to addition. Remember, if it is z comma dot, q comma dot, r comma dot, and the last one is c comma dot, are not groups, since for every element inverse does not exist. The inverse of 0 doesn't exist if any of the set have 0 as an element. So all these sets have identity element 1. So these sets are monoid. As I told you, this is a monoid. If we exclude 0, then we can form a group with respect to the operation of multiplication. If we exclude 0, then this q star denotes the set of all non-zero real numbers. So q means real numbers including 0, q star may be real numbers excluding 0, then we can give it a heading as group. So the set is closed with respect to the operation of multiplication, as the product of two non-zero numbers is again a non-zero number. So product of two non-zero, if x not equal to 0, 1 equal to 0, so xy is also not equal to 0. And 1 is the multiplicative identity and the inverse for every element. So p and q belongs to q star is q by p. Hence q star dot is a group. Moreover, it is infinite abelian group. Similarly, r dot, c dot, these are all are infinite abelian group. In the groups where 0 is not considered as an element. Okay. Next point. Remember that set of odd integers under addition is not a group. Set of odd integers under addition is not a group. Why? Because it doesn't satisfy the closure property. As sum of two odd, you can take 3 and 7, is an even, and the set of odd integers doesn't have the identity element as 0 is. So here if we take the identity element, so if you have to take the identity 0, but we are taking the odd. So whatever the identity element that has to be a part of this string, means the identity element has to be a odd number, but which is coming 0. So 0 is considered neither even nor odd. That's it. But if 0 is at the end, we consider it as an even. So here anyway, this is not being verified. So hence, the group of odd integers under addition is not a group. Okay. Next one. If we think about some advanced level of structure, then we can proceed like this. Let G. Remember that I am not trying to teach you any question right now. I am only going for the concepts, because these are the concepts which you never done or have done but indirectly. Okay. So let G be an abelian group with the following property, that if A, B, C belong to G and AB equal to CA, then B equal to C. So we need to check whether G is abelian or not. So AB, CA, B equal to C. So if we take C equal to B, then we can take AB equal to BA. And so this, with respect to this structural pattern, we can say, so AB equal to CA and CA equal to this part. So if we just replace C with B, so we can say AB equal to BA. Okay, remember that this C is being replaced by B here. So AB equal to BA, which is nothing but a property of abelian structure. So hence it's an abelian group. So very simple mathematics once you know the entire structure. Okay. Now, law of exponents for abelian group. How many exponents will be there? So let A and B are the elements of an abelian group, and let N be any integer. So in this case, AB whole to the power n, we know, just a simple mathematical rule. Okay, is it true for a non-abelian group also? If you ask me, then I can show you in a way. For example, AB equal to B, AB equal to AB we can write. Okay, as we are G is an abelian group, we are saying, which containing two elements AB, so AB equal to AB. So its square, if we take the square of this thing, this is AB into AB, so that is A, BAB, BA equal to AB, so AABB, this is A square, B square. So AB whole to the power m is, let this thing B to the power m. So AB whole to the power m plus 1 is AB whole to the power m into AB. So that is A to the power m, B to the power m, A, B. Okay, so if we take these two together, so A to the power m and A into B to the power m into B, so A to the power m into A and B to the power m into B, so A to the power m plus 1 into B to the power m plus 1. So very easy property by the principle of mathematical induction. We can say that AB to the power n is A to the power n, B to the power n, as its thing is applicable for 1 and 2 and for m and m plus 1 value. So for a non-abelian group, AB to the power n need not be equal to AN, BN for, need not to be equal for non-abelian. Remember that, this is a very important part. Now, there is the basic portions of this area is being done. Now we will go to some equivalence relationship structure. So in the equivalence, so let S be a non-empty set, then the relationship, this relationship is said to be an equivalence relation if it satisfies the following properties. First one is, it is reflexive, that is for all A. With this is symmetric, A to B, then B to A, and it is transitive, B to A, B to C, then A is also this. So reflexive, symmetric, transitive. Okay, so under this consideration we can call it as an equivalent pattern. So this congruent structure of this pattern will be introduced later as well. Okay, for example, for this we can use some of the arithmetical pattern, or modular arithmetic rather say. So you can check my modular arithmetic class on my website. See the modular arithmetic pattern. So if they ask you that what is the remainder of 3 to the power 400 upon dividing by 100, find the remainder. Okay, the answer is not 3, which coming into your mind maybe. Or maybe they ask you find the last two decimal places of 3 to the power 400. Last 3 to the power 400, last two decimal places. They don't want the last two digits. Okay. So how to proceed with this pattern? Okay. So we know 3 to the power 5, 43 modulo 100. Now why I've written this? Remember that how to read this. 3 to the power 5 is 143. So they say A, B mod C means if, I'm writing just normal, A is divided by C, then remainder equal to B. So if this value equal to 0, then A is exactly divisible by C. Let's see what happens. So 3 to the power 5, that is 143. Sorry, 243 is divided by 100. So leaving 43 as a remainder. 100 into 200. So 3 to the power 5, if we take a square, so according to the modulo structure, this will also be squared, keeping this thing unchanged. Then this is actually 3 to the power 10 and 43 square, whatever the last digits, 43 into 43 if we do. For this also I have a very shortcut pattern, okay, so that you can follow. So 43 into 43 is 1849. So that if we take the last two, so that is a modulo of 100. So 3 to the power 10, if we square it again, so this will be squared, and keep on doing it. And remember that 1849 and 1849 we don't have to do, only the last two digits. So that will give you, the last two digits are 4949, so 9 is 81 plus 2, so 01. So 3 to the power 10 square, so that is 3 to the power 10 square, that is 3 to the power 20 is leaving out with 01 with modulo 100. So there we are reaching to 400. So 20 into 20. So our target is somehow to reach this portion. So this is now 400, 01. So this is 01 to the power 20 is the thing. So hence the last two digit is, hence the remainder is 01, or the last two digits of the decimal places of 3 to the power 400 is also 01. So by this thing, the application is so easy. I'm giving you another example. So 2 to the power 50 is divided by 7. We need to find the remainder. So for this, 2 cubes. So what is the closest number more than the divisor? That is 8. So 8 divided by 7. So we can write the remainder is this. So modulo is 7. So this thing whole to the power 16 leaves you 148 modulo of 7. So 2 to the power 48, 1 modulo of 7. And if we just add 2 and make it multiply by 2, get 4 of modulo 7. So 2 to the power 50 divided by 5 is leaving a remainder of 4. So this is a remainder whose value is 4. So by basic modular structure also we can solve the question. So if you are asking about what kind of question is gonna come, so this is the kind of exact kind of a question that will be coming. So I can do another one here. For example, 2 to the power 1000 divided by 5. Okay, so 2 to the power 10, if we start, so in that way, so 5, so 2 square 4, 2 cube is 8. So 2 cube we can start with, 2 cube divided by 5. So this as this modulo of 5, and in that way you can proceed and find the answer and do it yourself as well. Okay, so now let's talk about some more group structure. In the groups you will see this notation many a time, z subscript n. So we have already seen that the set of integers from the group under the binary operation is an usual addition. So now let us introduce the new binary operation, addition modulo n, denoted by plus n. This is the binary operation plus n is defined as, for example, a plus n or b is nothing but a remainder r after dividing a plus b by n. This is the way to say it. So 5 6 of 7 means a remainder after dividing 5 plus 7 by 6. That's it. That is the basic structure, which is in this case 0. 7, 6 of 10 is remainder after dividing 7 plus 10 by 6, which is 5. So modular arithmetic will play a very, very, very important role. Okay. So here in this structural pattern, plus and subscript n. Okay, so this is called the addition modulo. This is called the addition modulo plus subscript n is a binary operation on z. Hence, if you see this is the thing given, is a groupoid. We can check that this plus subscript n is associative as a plus subscript n b plus subscript n c is nothing but a plus subscript n b plus subscript n and c, and both are equal to the remainder after dividing a plus c, a plus b plus c, this time a plus b plus c divided by n and the remainder value. Okay, next is another important thing. We will talk about the group based pattern. Okay, let me first solve one or two examples, or give the idea first. Okay, first thing coming to my mind is, for example, how to make the modulo pattern. If I have given you 1 2 3 4, so how to make the modulo, multiplication modulo of 4, okay, or 5, anything. So here we write mod maybe 5. Okay, so this is 1 2 3 4, 1 2 3 4. So 1 into 1 1. So if you divide by 5, remainder is 1. So till it is less than the modulo value, then whatever is the product, that is the answer. So first line is easy. Even 2 1s are 2, 2 2s are 4, 3 2s are 6, 6 divided by 5, remainder is 1. 4 2s are 8, 4 2s are 8, divided by remainder is 3. Okay, 4 1s are 4, this is 4, and then this is 3, 3 2s are 6, so 1, then 4, then 2, then 4, 3 2 1. That's it. So this is the modular arithmetic works into this. So 1 is the identity element, and every element has unique inverse, and multiplication of numbers are associative. So 1 2 3 4 forms a group under the multiplication modulo 5. So but additional modulo, so if we add 1 plus 1 2, 1 plus 2 3, 1 plus 3 4, so these values will be again in that same way will be considered, and we can decide whether it forms a group under the same modulo or not. For example, if we see that the set maybe 5 10 15 and 25, okay, 5 15 25 and 35, so let it be like 5 products. So is it group under the multiplication modulo maybe 40? So they are giving a multiplication modulo 40. So let's see what happens here. Okay, in this case modulo 40 is used. So here 5 15 25, and remember that it's a multiplication modulo they have said. So 5 15 25 and 35. So red is getting very dark here, so let's use something soothing to the eyes. Okay, now 5 5s are 25, so this is less than 40, there is no issue. 5 15s are 75 divided by 40, that gives you 35 as a remainder. 5 into 25, 125 divided by 40, 120, so it gives 5. This is 35 into 5, that is 175 by 40, 160, that is 15. In that way you can fill it up. 35 25, this is 25 into 25, so 365, so 15. So 35 into 15, which will be 525 by 40, so that is 5. So 25 into 125, again 5, this is 15, 25 and 35, okay, and 15, and this is 5, 35 and 25. Now if you see this set properly, in this set what is happening, each and every value is a part of the set itself. Okay, so this is a group under the multiplication modulo, and 25 is the identity element of the group. That's it. So this is a structure of element. So every element of 5, 15, 25 and 35 is the 5 times of the corresponding element based structure. Okay, so we can proceed with this further as well. Okay, in the new structural pattern. So let's go for the next one over here. Now one thing you need to know, that is what is this thing, what is UN5? So how they write this UN group, you get to see this U bracket N. So let us define a binary operation of a set of integers. Z is a multiplication modulo denoted by N. So A and B is the remainder after dividing AB by N. So this is the way of writing. It's very complicated and unusual, but anyway you have to write it. This is nothing but 18 divided by 5 gives you 3. 18 divided by 5 gives you 3. This is the way to write. So 11, not 6 of 2 is dividing by 6 gives you 4. So this is the pattern over here which we are going to follow in our questions as well. Okay. Even in case of matrices also we will do it, whether it is applicable or not, or the pattern is an ordered pair or not. Okay, it happens with, but it is mostly, it will be applicable for the square matrix structure. So being a square matrix will be a very important and typical pattern. So let's give one structural pattern. For example, A is a matrix called 1 0 0 and 1, and B is 2 1 0 and 1. So now the group may be this is 2 plus R is Abelian or non-Abelian if they ask you. Then what we can do, for example, here we need to find AB, which will be 1 is 1 2, then 1 just 2, this 2, and BA this to this, so this is 2 into 1, so plus 1 3. So in the first element we get to know that they are not, that's 1, so they are not same. So AB, this thing not equal to BA, so AB not equal to BA, so they obviously this is non-Abelian. Okay, remember that every kind of structure, each and every value falls into this categorization. So if you get to the categorization, so you know the pattern. Okay, now I will talk about a very interesting example over here. For example, there's a group table even like this: E, A, B, C, D, E, A, B, C, D. And the element based patterns are like this. For example, this is E, this is B, it's given. E, C, D, E, D, A, B, and nothing else. So how to fill it up? So they are saying E into E equal to E. Okay, E A, E A. So we need to find, is there any A E? So E A is the identity. E is the identity element over here. So E into A is obviously A. So E into B, B, E into C, C, E into D, D. That's it. Second line, A into E is nothing but again the identity thing coming, B into E, this, C into E. So in that way the first line is being done. Second line, okay, so if I mark it via the red, the ones I am filling it out, A and B. So we need to find what happens with B and A. So B and A, it is given C, so A and B, this pattern will be filled up by C because they have provided this. We don't know, but they have provided. Next, this element A, D. You see A and D is E. So D and A, the corresponding element, will also be E. So we put it E over here. Okay, so this is a way to finish it up. Now, this is different from the normal mathematics. That's why most of the cases abstract algebra is not understandable. Okay, so that's why I have chosen to not go with the problems but with the basic analytics over here. Okay. AC we don't know. Do we have CA? Yes, we have CA is D. So this is also D. Okay. Now C, B we don't have. Do we have BC? BC, yeah, it's E. So this is E. Next, BD. Do we have DB? Yes, D and B. D and B structure we don't have, and B and D we also do not have, so we will come to this later. But if we take into the pattern, every time A, B, C, D, E is coming, then A, B, C, D, E is coming, then B, C, D, E. So this has to be A. So B into D, A, and this here also D into B also be A. So D into C, do we have CD over here? Yes, it's B, so there we put B, and all the thing left is C. So this one is a crucial area here and here, because every time it's A, B, C, D, E. Even in the top left you go, every time A, B, C, D, E, A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. So now this thing are cross-checked. Now you are able to fill up a basic group-based table. Okay, it seems like a very hodgepodge thing, no information, nothing been provided, but this is the basic way to do it. Okay, so very, very important. So this will give you an idea at least that what actually happens in the group based pattern. Okay, so let's go for another one. Let's then say that A, B and C are the elements of a group. So now if they ask us to solve the equation AXB for X, and also A inverse XA equal to C for X. So in the first case, AX equal to P. So if we multiply A inverse, AX, B and B inverse, and here A inverse, C and B inverse. Just the way it has been first, last, first, last. Okay, change the color. Next part is A into this is nothing but identity. This is X, this is identity. So this is E again. This is A inverse, C, B inverse. So these two are gone. So X, A inverse, C, B inverse. Similarly, the solution of A inverse X, A with respect to C, we can also find it like A inverse of inverse. So it will be every time you put A inverse, C is C and A inverse. So overall it is A, C, A inverse for the value of X for the second equation. And this is for the first equation based pattern. So in this way you can solve any equation based structure also without going further into the